Okay, let's dive into this. For decades, we've all been told a pretty simple story about how airplanes fly or why a stream of water seems to hug the back of a spoon. But what if that story isn't the whole story? Today, we are peeling back the layers on a powerful and honestly, a surprisingly sticky force of nature.
So, let me just ask you, how does an airplane really fly? Now, if you're like most of us, an answer pops into your head involving air moving faster over the longer, curved top of the wing. It's what we all learned. But as we're about to see, that very common explanation has some pretty serious holes in it.
You've probably seen the classic demonstration, right? The Bernoulli strip. You take a piece of paper, you blow over the top, and poof, it rises up. The explanation we're always given is that the faster air on top creates lower pressure, so the higher pressure below pushes it up. And it seems to make sense, but it's a really misleading explanation of what's actually going on.
Or how about this one? The ping-pong ball that just magically floats in a jet of air. Again, the typical answer you'll hear is that the fast-moving air creates a low-pressure column that kind of traps the ball. This, too, is a classic case of mistaken identity. The real force at work in both of these examples is something way more interesting.
To find the real answer, we actually have to leave the physics classroom and travel back in time to a field just outside of Paris in 1910, where the answer was revealed in the wreckage of a revolutionary and, well, a very flammable aircraft.
What's so wild is that the basic idea was noticed way back in 1800 by a physicist named Thomas Young, but it just sat there, a little-known curiosity for more than a century. It wasn't until a dramatic plane crash that its true power was revealed to a brilliant Romanian inventor named Henri Coanda.
See, back in 1910, Coanda was testing the world's very first jet-powered aircraft. He wasn't even trying to fly. But when he fired up the engine, he was completely shocked to see the hot exhaust gases weren't shooting straight back. Instead, they were clinging to the curved wooden body of his plane. This weird stickiness set the wood on fire. The plane crashed, and right there in that fiery mess, the Coanda effect was truly discovered.
So what did Coanda actually witness? What is this bizarre force that can grab a stream of hot gas and pull it onto a surface so strongly it could bring down an airplane? Let's break down the actual physics of this sticky fluid effect.
So, in the simplest terms, the Coanda effect is just this tendency for a jet of fluid, air, water, whatever, to attach itself to a nearby surface and follow its curve. It's exactly why water from a tap will wrap around your finger, and it's the real reason that paper strip lifted up. So, how does it work? The secret ingredient here is something called entrainment. Just picture a fast jet of air shooting forward. As it moves, it actually drags the still air around it along for the ride. This action creates a little bubble of low pressure all around the jet. Now here's the really clever part. If you put a surface right next to that jet, you're blocking the air from rushing in on one side. So the normal air pressure on the other side is now way stronger, and it physically pushes the jet against the surface, forcing it to stick and follow the curve.
This is the absolute key takeaway. The air isn't just passively deciding to follow the curve. No, it is actively being forced onto that curve by a pressure difference that the jet itself creates. It's this incredibly powerful feedback loop, and that is the real magic behind the Coanda effect.
Okay, so now we have this really powerful principle. Let's take a look at how it's used in the real world, moving from something we all recognize, the airplane wing, to something truly mind-bending, computers that can actually run on air.
Now, this is where a lot of people get tangled up, so let's make this crystal clear. Entrainment, that dragging effect, is the cause. It's the spark that kicks the whole thing off by forcing the air to bend. Bernoulli's principle is a consequence. It's a great tool for measuring the pressure changes that happen because the flow has already bent. And viscosity? Well, that's just the limiting factor. It kind of determines how sticky the fluid is and when it's finally going to let go of the surface.
The most famous application is right here, on an airplane wing. You know those flaps and slats that extend out during takeoff and landing? They're not just there to make the wing bigger. They are specifically engineered to create these super curved surfaces that harness the Coanda effect to bend the airflow down as much as possible, which generates a ton of lift when the plane is moving slowly. That's cool, for sure. But what if you could take this exact same principle, a jet of fluid sticking to a wall, and use it to perform logic? I mean, to build computers that have absolutely zero moving parts.
Well, welcome to the incredible world of fluidics. This is a technology that completely replaces electrons and mechanical switches with jets of fluid. We're talking air, water, you name it, to perform complex control and even logic operations.
Now, you might be asking, why would you ever do that? Well, just look at the comparison. Electronic systems, they have parts that can wear out. They're vulnerable to intense heat, to radiation, to interference. Fluidic systems, they have none of those problems. They are practically indestructible, which makes them absolutely perfect for the harshest environments you can possibly imagine.
So how does a fluidic switch actually work? It is just genius. A main power jet of air flows into a little chamber. Thanks to our old friend the Coanda effect, it immediately latches onto one of the sidewalls. That's your off state, or your on state. So how do you flip the switch? All you need is a tiny little puff of air from a control port on the other side. That little puff is just enough to break the low-pressure seal, and it instantly forces that powerful main jet to flip and stick to the other wall. You've just flipped a bit from 0 to 1 with absolutely no moving parts.
And here's the really magical part. A tiny puff of control air, with just a tiny fraction of the energy, can redirect a power jet that's more than 100 times stronger. That, my friends, is amplification. You're using a tiny signal to control a huge amount of power. It's basically a transistor, but it's made of nothing but air.
And this is not just some historical curiosity. This powerful, parts-free technology is quietly making the future of control systems possible in some of the most advanced fields, both on and off our planet.
The applications today are just amazing. In medicine, there are microfluidic chips that use these exact principles to sort individual biological cells. In aerospace, engineers are designing smart wings that use tiny, precise puffs of air to steer an aircraft instead of using heavy mechanical flaps. And in the most extreme places you can think of, like inside nuclear reactors or on deep space probes where you absolutely cannot send a repair person, these indestructible, part-free systems are the only things you can truly count on.
So, I want to leave you with this thought. We usually think of progress in terms of silicon chips and lines of code, but the Coanda effect shows us that some of the most elegant, most robust solutions are hiding in plain sight, in the basic physics of how things flow. It just makes you wonder, what if the next great revolution in computing isn't written in code at all, but is sculpted by the flow of air?